This video demonstrates the techniques for flying a precision instrument approach in light airplanes and jets. In prior videos, we looked in detail at the basic pitch transition rules, which cover the procedures for changing airspeed at a constant flight path, changing flight path at a constant airspeed, and changing both flight path and airspeed. An example flight showed these basic rules in action. These videos are listed at the bottom of this page. In this video, we will apply the flap and gear rules to instrument approaches in light airplanes and jets. In the previous flap and gear rules video, we found that going from the clean configuration to the landing configuration before landing, aerodynamic principles dictated that it was best to extend flaps to slow down and to initiate the final descent by extending the gear. The first choice for flap extension is during a non-precision descent. However, since flaps are extended at particular points during an approach, this first choice is not always available. The second choice of extending flaps during level flight is not a problem if flaps are extended in increments and the airspeed is allowed to stabilize before applying the next flap setting. There are some differences between light airplane and jet instrument approach profiles. Since the light airplane instrument approach profile is the least complex, we will cover it first. Beginning in level cruising flight at 170 knots and 4,000 feet, we begin a cruising descent by reducing pitch attitude from 0 degrees to -2 degrees and manifold pressure from 23 inches to 20 inches. Turning to our final intercept heading for the localizer, we continue the descent to 1,500 feet. Approaching 1,500 feet, we level off by returning to 0 degrees pitch attitude and 23 inches of manifold pressure. We now begin to slow down by reducing manifold pressure to 19 inches and increasing pitch attitude slightly as the airspeed slows. At 155 knots, we are below the max flap extension speed for approach flaps, and we'll select them now. Maintaining the pitch attitude at 0 degrees, the airspeed slows and stabilizes at 120 knots while we turn onto the localizer. This simulation shows a similar airplane approaching the glide slope. Notice that intercepting the glide slope by extending the gear and making a precise pitch attitude and power change captures the glide slope immediately and allows the approach to continue at the same airspeed. We are now approaching the glide slope at 0 degrees pitch attitude and 19 inches of manifold pressure. As the glide slope needle centers, we select gear down and set the pitch attitude to -3 degrees and reduce the manifold pressure to 17 inches. The glide slope is now captured and the airspeed remains at 120 knots. Small pitch attitude changes are now used to maintain the glide slope, and small power changes are used to keep the airspeed at 120 knots. This airplane's normal approach speed is 90 knots, but 120 knots is used to keep up with jet traffic. This means that most light airplanes will be flying ILS approaches with partial or no flaps. The landing can be made from this condition as shown here, with a resulting long landing distance. This is not a problem since most ILS runways are long enough to accommodate jets. An option during an approach with high ceilings and good visibilities is to apply flaps and slow down after entering visual conditions. However, there is a problem if full flaps are extended without a change in power, due to the size of the bump caused by the increased lift as flaps are extended. Notice the long landing distance in this case. If we elect to apply additional flaps and slow down after entering visual conditions, reducing the thrust to idle prior to extending full flaps will considerably reduce the size of the bump and reduce the landing distance as well. As the airspeed approaches the normal approach speed of 90 knots, 16 inches of manifold pressure is added in order to maintain the speed until flare. If the airspeed is at or above 90 knots at flare height, no added power will be necessary. This method results in a minimum landing distance, as shown here. Now let's look at a 120 knot partial flap landing in low visibility conditions. We've stopped at the 4th intersection. Next, let's look at the option for higher ceilings and good visibility. After becoming visual, we will reduce thrust to idle and select full flaps. As the airspeed approaches 90 knots, we increase manifold pressure to 16 inches in order to maintain the airspeed. After completing the landing, we are stopped at the 2nd intersection. Now, let's look at the instrument approach profile for jets. There are several areas unique to jets that do not apply to light airplanes. Specifically, jets have a maximum operating Mach number, they have less speed stability, and jets are normally operated with the operational limitation that the entire final approach will be stabilized in the landing configuration. Let's look at the maximum operating Mach number first. The first question that is usually asked is, why is there a limiting Mach number when supersonic airplanes can fly well above the speed of sound? The reason is that supersonic aerodynamics dictate a very different design for supersonic airplanes compared to subsonic airplanes. Also, today's supersonic airplanes are much less efficient and uneconomical compared to subsonic designs. Therefore, practical airplanes are subsonic designs that operate close to the speed of sound. The problem is that the airflow around parts of the airplane can be faster than the speed of the airplane through the air. Close to the speed of sound, some of the airflow becomes supersonic. These mixed areas of subsonic and supersonic flow can cause control problems and buffeting. The maximum operating Mach number, or MMO, is established to keep subsonic airplanes out of these transonic flow effects. This graph shows altitude versus indicated airspeed. Specifically, this is the airspeed displayed on the jet's airspeed indicator, where any errors have been corrected by the jet's air data computer, so that indicated airspeed is purely a combination of true airspeed and air density. This airplane has an MMO of 0.9, based on transonic flow effects. In addition, there is another limit called maximum operating airspeed, or VMO, which is an indicated airspeed limit to prevent any structural damage. VMO for this airplane is 390 knots. During a climb at constant indicated airspeed, true airspeed increases to balance the decrease in density. Mach number is the ratio of the true airspeed to the speed of sound. The increase in true airspeed during a constant indicated airspeed climb, combined with a decrease in the speed of sound as the temperature decreases, means that the Mach number is also increasing with altitude. Indicating 390 knots at sea level, the true airspeed is also 390 knots. So the Mach number is less than 0.6, well below 0.9. Climbing at 390 knots, the true airspeed and Mach number increase. Slightly over 21,000 feet in the standard atmosphere, the Mach number has increased to 0.9. To avoid exceeding this limit, the indicated airspeed must be reduced to keep the Mach number at 0.9 as the climb progresses. The graph shows that this airplane is airspeed limited at low altitudes, since remaining below Vmo guarantees being below Mmo, and is Mach limited at high altitudes, since remaining below Mmo guarantees being below Vmo. Most subsonic jets find their Vmo and Mmo values coincide in the low 20,000 foot range. Below this, climb, cruise, and descent speeds are expressed as indicated airspeed, while at higher altitudes they are expressed as Mach numbers. In this way, the actual speed is easily compared to the relevant limit at that altitude. Next, let's look at speed stability. This graph shows drag versus airspeed at various flap settings for a typical jet transport. Light airplanes operate mostly on the steeper slope of the right-hand side of these curves. In this area, any changes in speed produce drag changes that tend to drive the speed back to the original value. But because of their cleaner design, jets flying in the terminal area during approach operate near the speed shown by the circles on the graph. Since these speeds are in a relatively flat spot on the drag curves, many nearby speeds require almost the same thrust setting. This means that if an airspeed error occurs, it will not be corrected automatically. To correct an airspeed error in this flat portion of the drag curve, it is necessary to overpower or underpower, wait for the desired airspeed, and then reset the correct power setting. This is second nature to military pilots that were originally trained on jets, but requires conscious thought during jet training for civilian pilots initially trained on propeller-driven light airplanes. This jet is cruising at 39,000 feet at Mach 0.8, indicating 250 knots. True airspeed is slightly below 460 knots. The striped needle, called the barber pole, is indicating 265 knots, which at this altitude is the indicated airspeed at Mach 0.86, which is the Mmo for this airplane. Staying below the barber pole guarantees that both Vmo and Mmo will not be exceeded at any altitude. We are now entering a Mach 0.8 descent at idle thrust. Note the increase in indicated airspeed during the constant Mach descent. As the airspeed approaches 300 knots, we transition to holding airspeed rather than Mach number. Note that the Mach number is now decreasing. The barber pole reaches its maximum value of 365 knots around 25,000 feet, where it will remain at lower altitudes. Note that the Mach number is now below 0.72. At this point, we increase the pitch attitude in order to slow down to 240 knots to stay within the United States 250 knot speed limit below 10,000 feet. We are now approaching the final approach course in a 240 knot descent. Turning to the final intercept heading, we call for flaps 1 and slow to 200 knots. Intercepting the localizer course, we call for flaps 5 and slow to 180 knots. After leveling off at the glide slope intercept altitude of 3,000 feet, we call for flaps 15 and slow to 160 knots. At this point, we are prepared to accomplish the final approach configuration and intercept the glide slope. Since the intercept procedure is more complex than the light airplane case, let's examine it in detail before continuing the approach. This would be the ideal intercept for a jet, which needs to be in the full landing configuration and stabilize at the final approach speed for the entire final approach. Full flaps are selected and the speed is slowed to the final approach speed of 140 knots prior to glide slope intercept. The landing gear initiates the descent and the new pitch, attitude, and power setting immediately capture the glide slope. The problem is, if landing flaps 25 and 30, are selected before gear extension, a gear up warning will sound. Some older jet transports could use this procedure because they had a switch to disable this warning. Since this is no longer common, we have to modify the procedure. If we approach the glide slope with the last pre-landing flap setting, flaps 20, and then fully extend the landing gear before selecting flaps 25 and flaps 30, an altitude loss will occur prior to glide slope intercept unless a pitch attitude change is made. We would prefer to not make any pitch changes during manual flight. A solution to this problem is to approach the glide slope with the flap set 1 notch prior to the last pre-landing flap setting, which is flaps 15 in this case. Then, gear down and flaps 20 are selected simultaneously. A flight path bump from the flap extension cancels the altitude loss caused by gear extension, and no gear warning is sounded. When the gear is full down, flaps 25 and flaps 30 are selected, and the glide slope is captured with a change in pitch, attitude, and power. In this example, we see that the same procedure can be applied with the autopilot engaged in altitude hold mode. The only difference is there will be several minor pitch attitude changes. Let's see how the glide slope intercept works in practice. Gear down and flaps 20 are selected simultaneously. Flaps 25 and flaps 30 are selected when the gear is full down. Then the final approach pitch, attitude, and power are set. Now, pitch changes maintain the glide slope, and thrust changes maintain the airspeed at 140 knots.